Okay, to explain what's going on here, I always like drawing it so I've got an extension within it. At the moment it's drawn it here when it's 0.4, and the natural length of the left hand one is 0.4. So I want to draw it a little bit further to the right there. So now I've got an extension within it, because now I've got the 0.4 there, and I can have an extension in there of x, and that's going to define my positive. So I now got that's going to be my direction, so that'll be x double dot, my acceleration there. Squiggly line to show I've got a string or a spring, and the same here. And this is made up of 0.4 meters and an extension x. And this one here is made up of 0.6 meters, that's its natural length. And then it's got to go, the extension is this bit here. And so the whole gap between there, that's 1 meter. The whole thing's 1.5 meters. So that bit will be 0.5 meters. That'll be 0.5 minus x in that direct thing there. Okay. And now I know that the greatest kinetic energy will happen when it's basically when it's going fastest, will happen at equilibrium point. So at some stage, I'm going to have to find the equilibrium point. So I might as well do that early on. And so I've got here T tension there and a tension that way. Tension equals lambda times the extension over L. This one equals lambda times the extension over L. Not particularly nice maths because I've put x for both of these, but that does not mean it's x. In this formula for me, it means it's the extension. So if I want to put it in properly here, this is lambda, and the lambda for this one is 15, times by the extension, and the extension of this one is 0.5 minus x, over L, and the natural length is 0.6. So that's done the tension of this one, and the tension of this one will equal lambda, and lambda for this one is 20, times by x, well actually it is x, because that's why I set it up, over L, and that is 0.4. So I need to find the equilibrium point. So for the equilibrium point, I'm going to have to resolve horizontally, and the force to the right must equal the force to the left, or the other way around. So what I'm going to have is the tension, which is 20x over 0.4, must equal the tension going the other way, which is 15 times 0.5 minus x, all over L, which is 0.6. 25 0.4, that's 75x equals, that's 25 times 0.5 minus x, so that's minus 25, that means that's not, that's 50, I've missed the line, that's 50x, and now add 25x, that will give me 75x equals 12.25, and so x equals, that'll be 1/6 of a meter. So I now know where where the equilibrium is at that point there, and I know that's where the maximum kinetic energy will happen. So I can find out what's going on here. And as all these things, total initial energy equals total final energy, and unless there's a collision, it's not here. Final energy. And this energy is made up of two things. It's made up of elastic potential energy and kinetic energy. And so is this one, elastic potential energy and kinetic energy. And the elastic potential energy, we got A and B, and then we got A and B. And our kinetic energy is a half mv squared. I want to write that down. And elastic potential energy is lambda x squared over 2L. I want to have that written down, at least somewhere, because it's so easy to forget the squared or something, but I have the formula written down, I can just do what it says. So for A, to start off with, is initial energy, where its natural length is 0.4. It was 0.4, so that's going to be 0, plus the elastic potential energy of the B, it's lambda, which is 15 for B, times by the extension, which initially was when x was 0, so that'll be 0.5. So 0.5 squared all over 2 times 0.6. And it's released from rest, so A and B, the kinetic energy is 0. And now what's that comes to? Elastic potential energy we need to work out of A and B. So A is the easy one because now it's been stretched by 1/6. So that'll be lambda, I'll write the formula down over here as well, lambda x squared over 2L. So lambda 20 times by x squared, so that's 1/6 squared over 2L, that's 0.8, plus for B, lambda 15. The extension is 0.5 or half minus a sixth squared all over 2L, that's 1.2, and plus the kinetic energy. And that's kinetic energy of A and B, and that's it's the kinetic energy of just this particle B. I don't know why I had A and B here, because it's only making 2 strings, there's just one particle. So forget that. It's just plus 0 because it's released from rest. And this is kinetic energy of that particle. And that's what I want to try and find. And this, if I work these out, it gives me 3.125 equals 0.6944 plus 1.3888 plus the kinetic energy. And so the max kinetic energy, which happens at the equilibrium point, equals 1.04166666, etc. joules. You can round that. If I get round to it, I will correct this mistake here, but that does happen at times. And that's question 4 done.